All right, today is November 22nd, 2011. We're working on lesson 5.2. We have the same idea for our objective today. The only difference is we're going to be setting up word problems, which is one of the more difficult things in this chapter. So we're going to be using the same trig ratios for right angle triangles. We're going to be working with just right angle triangles again today. Example 1 says a surveyor stands at point S. Okay, so we have our surveyor. He's at point S. Okay, and uses a laser transit and marking pole to sight two corners A and B on one side of a rectangular lot. So there's a rectangular lot he's facing, and there is a point A and a point B. Okay. Actually, let's flip it around. This is a rectangle right now. We have point A and B. The surveyor marks a reference point P on a line AB that the line from P to S is perpendicular. So what he's saying is from where he is, he marks another point that is straight, that makes a perpendicular line from AB, or in other words, it makes a right angle. Okay? So the line he marks creates a right angle with line A and B on both sides. Corner A is 150 meters away from S and 34 degrees east of P. Okay? So it's 150 meters away. And they've also said that it is 34 degrees east from where we are. Let's make that a little more clear. That's 34. It's 34 degrees and it's 150 meters away. It also says that corner B is 347 meters away and 69 degrees west of P. So first off, we have to have a relatively good grasp of our directions. This is going to be 69 degrees west, and it's 347 meters long. So quickly, we know that, and if it's a good idea for you to mark down, we have our north, south, east, and west. We're going to be finding the distance of line AB. Okay, so the surveyor wants to find the distance between line A. So, just like we said before, we have a right angle triangle. In fact, we have two of them. There's one here and another one here. They're outlined like this. In order to find the actual distance of line segment or the side of the triangle AB, what we're going to need to do is we're going to need to add the two bottom parts of the triangle together. So in other words, we're going to call this side X and this side Y. In order to find line AB, we will have to add X plus Y together. Now that'll be our final step. First, we actually have to find the distances of X and Y. So I'm going to work with these as one triangle at a time. We'll go to another page. Okay, so like we had in our first triangle, if you remember, this was our point S, point P, and this was point A. A was 150 meters east and 34 degrees east of point S. We're looking for what we called Y, side Y. So because I have angled 34 degrees, this angle here, I have to refer to the two sides I'm using. This is considered what? Opposite. So this is our opposite side, and this would be considered our hypotenuse. Okay? So in other words, when we go over to our ratios, we need something that deals with opposite and hypotenuse. When we go over here, what do we get? We're going to sine law, or not sine law, sorry, sine ratio. So, we have our sine ratio. We're going to be replacing theta with 34 degrees. So we have sine 34 is equal to, we're looking for the opposite, so we're going to call that y. And the hypotenuse is 150. To isolate y, we bring 150 over. Now, because this says divided by, when it goes to the other side, it has to become multiplied. So we get 150 times sine 34 is equal to y. We're going to plug this in. It's okay. In a calculator it will. Sine 34 is 0.559 times 150, 83.8. So, side y is 83.3 meters. Okay. As long as you do it in the proper order. If you follow bedmass, you'll be fine if you don't put the brackets in. Make sure you follow bedmass, though. That's our first triangle. Our second triangle, 83. Sorry, my mistake. It said right there. I'm not sure why I read it wrong. 83.8. Yeah, we could round to 9 if you guys like. All right, let's work on our second triangle. All right, our second triangle. S, point S to point P, and this time we had point B. The distance from S to B was 347 meters, and the angle west was 69 degrees. Again, we are looking for our side X, we called it. It's the exact same. We have a hypotenuse, and we have our opposite side. So we'll be using our sine ratio again to solve this. So, for theta, we're going to plug in 69. We'll go a little quicker. Our opposite is x, but our hypotenuse is 347. When I move it to the other side, we get 347 times sine 69 equals x. And sine times 347. 323.9 or 324. 9 meters, okay? Or if we round it, you're right, it's 324. So, I have my side x and y. We have those measurements of 83.3 and 324. We're going to go back to our original page and add them together. So, A and B was equal to, we remember x was 324 and y was 83.8. 9? Sorry. We add our two together. And we get 407.9 meters long is our distance. Example number 2. Karen is a photographer in a helicopter. She is 720 meters above the bridge. So this is our bridge. We know that the helicopter is 720 above the bridge. It says that she is 1 kilometer horizontally from the west end of the bridge. So remember, this is our west, this is our east. So where she is, she's 1 kilometer. And the entire bridge is 2,650 meters. The very first thing we need to do is we need to be working in one specific unit. Now, since I have something that is less than a kilometer, I'm going to try to work in meters. So 1 kilometer is equal to 1,000 meters. So we're going to change this. And since the distance from here to here is 1,000, and we know the total distance is 2,650, our other distance will then be 1,650 meters. Okay? So we know how far she is from the left or the west and east ends of the bridge. Now, what we need to figure out is we need to figure out actually the angles of depression is what the question's asking. It says, what are the angles of depression to each end of the bridge? Now, an angle of depression is drawn like this. An angle of depression is drawn off a horizontal line. So in other words, this horizontal line to the east end of the bridge. Okay? So we're actually looking for what we would think we're looking for. The angle of depression is going to be this angle here, is what we're trying to find. So we can call that, we'll call that our X angle. Okay? We're also looking for the angle of depression to the west end of the bridge. They're not asking us to. The other angle of depression. All right, the other angle of depression we're looking for would be this angle here. Remember, an angle of depression is drawn off a horizontal line. So we're not actually looking for any of the angles inside the triangle. Problem is, we're probably going to have to find them in order to find angle of depression. Now I can find all the angles in here. There's also one other trick to this question, if you remember your angle rules. Does anyone know where in the triangle or what angle in the triangle would be equal to this angle X? Brendan. That's right. That Z formation, that's right. What we have here is this X angle here is actually going to be the exact same as this one here because we have two parallel lines. Now, if you didn't know that, that's fine. You can still solve for it the other way. And what that also means, this could be our X. That also means this would be an equivalent for our Y. Okay? So what we'll do is we'll find it the original way, we'll say, without the shortcut, and then we'll prove that the shortcut works. We're going to solve, now, in the other one, what I would prefer to do is I would solve for these angles and then subtract from what? From 90 degrees. These are creating 90-degree angles. Okay? So what I'm going to do is I'm going to find those two angles there and subtract from 90 for both of them. Exactly. So let's set this question up on another page so it's a little cleaner. All right, so our first triangle from the helicopter was 100 meters to the west end of the bridge, and it was 720 meters above. We're looking for this angle because we know that our angle of depression will be that angle minus 90 degrees. Okay? So, again, because I'm looking for this specific angle, I have to verify what sides of the triangle I have. What side would this be considered? That's right. And the other side would be adjacent. So which of the formulas will be, or which ratio? We're looking for our tan. Okay. So in this case, we're actually looking for the angle itself. So we'll call that tan theta or x, whatever you feel comfortable with. Our opposite side is 1,000, and our adjacent side is 720. We're going to end up with tangent theta is equal to 1,000 divide 720, 1.39, we'll say. 1.39. Now, we're isolating for theta itself, which means I need to bring tan to the other side. So when tan goes to the other side of the equation, that's right, we look for the inverse of that. So we'll have theta is equal to the tangent inverse of 1.39. 54.3 we'll round it to. Perfect. Okay, so because we do have this measurement now, being 54.3, we know that this creates a right angle triangle. So for our angle of depression, we need to take that right angle, which is 90 degrees, and subtract our 54.3. 35.8 degrees. Okay? Now, just to prove that this works, we have a triangle. We have two of the angles. What do all angles in a triangle equal to? That's right, Michael. All the angles in a triangle are going to equal to 180 degrees. I have this measurement here, which is 90. So if I subtract 90, I'm going to call this our blue angle, okay? This is going to equal the blue angle. And our other one was 54.3. Because I'm subtracting my other two angles, I'll be able to figure out this angle here. So 180, subtract 90, subtract 54.3, 35.7. So if you guys noticed, our blue angle is 35.7. Yeah, it's fine. That angle here ended up being the exact same measurement of our other angle of depression. Okay, the other side of the triangle, 1,650 meters, was it? Yeah, 1,650 meters away. The helicopter was 720 meters, and we were trying to find our angle of depression, which was right here. In this example, what we'll do is, since we know that our rule, this will be the exact same. Since that'll be the exact same as our other angle up here, I'm just going to solve for this one, so I don't have to subtract by 90 at the end. So, since I'm now working with this angle here, the measurements I have are the opposite side and adjacent again. So tangent theta is equal to our opposite, which is 720, divided by 1,650. So we get 720 divide 1650, 0.43. 436 we'll say. When we bring tangent to the other side, it becomes tangent inverse. So the inverse of this becomes 23.5. So you would push shift usually on your calculator. You don't have that option. So our two angles of depression are 35.7 degrees and 23.5 degrees. Okay, so you are at a mini putt, and you're on the third hole, and there is a pendulum blocking the hole. The pendulum is 10 meters long. It moves back and forth, the pendulum. Okay? So the ball needs to go into the hole, and the pendulum is swinging directly in front of you back and forth. Okay? The pendulum is 10 meters long, and your ball, let's say, is 50 centimeters in diameter. It's huge. Okay? We're going to say the pendulum has swung. Okay, so our pendulum, when it swings, it still stays the same distance. It's still 10 meters long. The only difference now is it's moved 15 degrees from when it's standing still. What we want to figure out is if this ball is going to fit under the pendulum when you putt it. Okay, so it's now moved 15 degrees. We need to figure out the difference in height. So I need to find out how high off the ground it is right now. Okay, so because it's at it's still 10 meters long. Imagine this pendulum has swung. This is when it's standing still. It's 10 meters. This is how high it is. When it swings 15 degrees, it's up here. And in other words, we need to figure out, we're going to create a right angle triangle here. Our right angle triangle is going to be here. We're going to figure out how far or how high off the ground this is. Okay, so according to our rules, we know this is 15 degrees. And remember, we have a Z pattern, so we know that this is also going to be 15 degrees. We know the hypotenuse of our new triangle here is still going to be 10 meters. It doesn't change in distance, this pendulum, at all. What we're going to have to figure out is how long this part is. This will essentially tell us how high off the ground we are. Okay, this distance here. So we know that we're still 15 degrees. Okay, so we need to find out the height here. Okay, we need to find out this height here. Our hypotenuse is 10 meters. We're looking for this height, so we'll call it x. Now, in order to find this, we got to set up a ratio. We have this angle, which is 15 degrees, and we have the hypotenuse. What side is this considered to the angle? That's considered the adjacent side. We know the hypotenuse is 10. We don't know how far off the ground it is, though. So, if our angle is 15, so we have cos 15 degrees. We're looking for the adjacent side, which we'll call x. And we know the hypotenuse is 10 meters. Okay? We need to solve for x, so when I bring 10 to the other side, it's multiplied by. So we have 10 times cos 15. 15 cos times 10. 9 point, let's do it exact, okay? So our x is going to be 9.65. So now what we figured out, in terms of our pendulum, we know the pendulum was exactly 10 meters till it hit the ground for that hole, and our ball is 50 centimeters. If 10 meters is the distance to the ground, and this is now 9.65 centimeters. Oh, sorry, not centimeters, meters. We need to figure out if the ball is going to fit under the pendulum when it's 15 degrees from the center. So, if the original pendulum is 10 meters, okay, and we're subtracting 9.65 centimeters, this will tell us how much room is left. So that's this area here. We subtract, we get point.
There are 3 spots left on the